Hi everybody, this is James Tompkins and welcome to Lecture 2 of the Corporate Finance series. Actually, this is Lecture 2A and 2B because I'm splitting this topic, time value of money, into two parts. And before I get into the agenda, and I'll show the agenda of both of those, I want to show you, if you will, the outcome if you're one of those brave souls that sticks through both Lecture 2A as well as Lecture 2B. So here's an example. I'm not going to read through all of it. You can look at it and take a snapshot or pause it or whatever, write it down. But here's an example of what I would consider to be a problem that if you can do this, then you can probably do anything in time value money. I mean, there's two different levels of understanding. You can have a knowledge, I'll use that word specifically, of knowing what buttons to push on a financial calculator or knowledge of knowing what functions to use and so on and so forth. But that's not the same as an understanding of why you're doing what you're doing. And in my opinion, if you can do this problem, it's very likely that you understand why you're doing what you're doing. And that's my goal in these next two lectures, 2A and 2B, to raise your level to one of understanding this topic, as opposed to, well, here's a formula and throw in the numbers and out pops the answer. So if you like, try this on your own, before you even do any of this, and you use a financial calculator if you want, use a spreadsheet if you want, and I'd be surprised if you can do it even with those tools. And I could easily be wrong, but either way, I hope you'll benefit if you choose to go through these two lectures from an understanding perspective. Here's another problem, not quite as challenging in my opinion, but still relatively challenging. You need to have an in-depth understanding to do this one, and so if you like, you can try it with this one too. In any case, by the end of Lecture 2B, I'll be going through both of these problems. And in my opinion, best case scenario, you'll be able to do those on your own before I go through it. And worst case scenario, when I go through it, you'll be understanding it and not having, if you will, a memorization level of knowledge. So, having said that, I'll start off the way I usually start, and that is with an agenda. And basically, this particular lecture is going to focus on single cash flow principles. Okay, I mean, I'll discuss the purpose of any time value of money formula and a couple of definitions. And by the way, when it comes to definitions, is that something you memorize or is that something you understand? Well, that's actually something that you memorize. For example, I've memorized that the sky is called the sky. I don't know why the sky is called the sky. I've memorized that. So definitions you memorize, but concepts you understand, and formulas you understand because that would be based on derivations and so forth. Then in Lecture 2B, and 2B builds on 2A. In other words, it's very difficult to understand Lecture 2B unless you have a solid understanding of 2A. And this is where I'll get into multiple cash flow principles, and I'll do those two challenging examples that I brought up. So that's where we're headed, and I hope you'll stick with it. So what's the purpose of any time value of money formula, and why have a model for measuring value? Well, let me put it in two contexts. First of all, do you remember what I said the theme of this class was? This is in Lecture 1. Well, basically, financial principles as it affects firm value. And so that's why this is basically the first topic. If you're going to manage value, does it help to be able to measure value? It does, right? So, for example, if you go on a diet, what's a really useful instrument to have to see if your diet's working? A scale, right? I mean, that way you can see not only how much you're, whether you're gaining weight or losing weight, but also how much you're gaining or how much you're losing. And therefore, how effective is whatever you're doing with respect to, your weight going in the direction that you want it to go in. Okay? But there's also another perspective. So, for example, suppose I said to you, hey, all right, I can see that you're a really nice person. All right, so I'm gonna give you $1,000. Now, is that happy face or sad face? Well, presumably that's happy face, right? $1,000, okay? Now, what could I add to that sentence that might turn happy face into not so happy face, maybe in sad face? Well, no, I'm not applying any conditions, and it is a gift, and so you don't have to pay me back. Well, what about this? What if I said, all right, I'm going to give you $1,000, but I'm going to give it to you in my will, and I'm going to live a long time. I've got maybe another 40 years to go, whatever. So would you be as happy? You wouldn't, right? So what that means, or what that illustrates, is that money has two dimensions. It's not good enough just to talk about the $1,000. You also have to talk about, well, when? Okay, money has two dimensions. I mean, if nothing else, could you put a dollar that you have today in the bank and have it make interest? You can, right? And so, therefore, what will any time value of money equation do for you? Well, basically, move that dollar amount into different time periods. So, for example, maybe, and here's a cash flow timeline diagram. This is our first one, so I'll explain it. So the things on the bottom, those represent time periods. Okay, 0 is typically today, but does it have to be today? No, it can be anything you want. What about how long these time periods are, like from time 0 to time 1? Does that have to be a year? No, it can be anything you want. It could be 1 second intervals, it could be 2.5 year intervals, it could be whatever you want, right? In any case, what's on top is $10. So if this is today times 0, and if these are years, this would mean, hey, 1 year from today, I expect to get a $10. And so what will any time value money equation do? Well, it'll take this $10 and it'll move it any way you want along the time diagram. So for example, what is it worth at time period 3? And that's what we'll be doing in this single cash flow principles. Be able to move the $10 anywhere you want along the timeline diagram, as well as get into other details about single cash flow principles. Okay, so let me get into two definitions. And as I mentioned, definitions, is that something you memorize or something you understand? Well, that's something you memorize, right? Okay, so what is an effective periodic rate, which I'll denote as R? Well, either you know it or you don't. So basically, it's the amount of interest made for $1 after one period. So as an example, let's say I deposit $1 today, and 6 months later, I have $1.05. Then what is the effective 6-month rate? Well, I made 5 cents off the dollar, and so it's communicated on a percentage basis, so basically 5%. That would be my effective 6-month rate. Okay, one more definition, and that is the nominal or stated or advertised or annual percentage rate. Those are all different names for it. And let me give you an example. Suppose a bank advertises that it pays 10% compounded semi-annually. Okay. Well, that is the nominal, stated, or advertised rate, or the APR. Because unless something says, hey, this is an effective 5-year rate, or this is an effective 3-month rate, or whatever, you have to assume that it is this guy right here. This is our stated or advertised rate, and that's just by convention. In addition, this is an annual number by convention. So what do you do with this? Well, let's take a look. Say a bank advertises that it pays 10% compounded semi-annually. Well, by definition, not by understanding, but by definition, there's only one first step that you can take with that 10%. Do you know what that is? Well, basically divide it by 2. Why? Because there's 2 6-month periods in a year, and the 10% is annual by convention. And now, once you've divided the 10% by 2, now by definition, you have an effective 6-month rate. So when a bank says, hey, we pay 10% compounded semi-annually, the only first step I can do with that 10% is divide it by 2. Now I have 5%, and now by definition, that is my effective 6-month rate. So what is the effective 6-month rate? What does that mean? What will $1 grow into? Well, it'll grow into $1.05, right? And after how long? After 6 months. In any case, those are the two definitions that you need as we go through all the ongoing or future time value money formula in both Lecture 2A as well as 2B. So let's get into single cash flow principles. And basically this refers to, as I mentioned at the beginning, that $10 that was at time 1, and how can we move it to time 3? Basically, it refers to moving a single dollar amount anywhere along the timeline that you want to. And it turns out there's only one single cash flow formula. So let's derive that. How about your first pop quiz? Oh, you like that, right? Because I can't really give you a pop quiz under these circumstances. But seriously, I'm going to illustrate to you that you already know this formula. Okay, at least I think I am. So let's say you deposit $100 with the bank today, and they say, hey, we'll give you 10% interest in 1 year. And the question is, how many dollars will you have in 1 year? So in other words, you have $100, 10% interest, 1 year later, and 10% interest over the course of the year. 1 year later, what has it grown into? Well, I'm guessing that you probably said 110. That's what I'm guessing. Okay, so $100 today. In this case, I said that you made 10% of interest in 1 year, so the effective annual rate was 10%. And how did you calculate it? Well, what you probably did was you said, all right, well, I began with my original 100, and I took 100 times 10% to get my interest, and that came to a total of 110. So in other words, the future value was $110. So when I move this $100 forward one period, then what did I multiply it by? Well, in the end, I multiplied it by 1.1, right? Because 100 times the 1 is what we began with, plus 100 times the 0.1, that's the $10 of interest, that gave us the 110. So basically, to move it forward, the $100 forward one period, I multiplied it by what? 1.1. Well, what if I wanted to move it forward another period? What would I multiply it by? Well, presumably 1.1 again, right? So in other words, to move the $100 forward 2 periods, I'd multiply it by 1.1 right here to get it to 110, and then 1.1 again to get it to 121. And so if you can understand that, I don't mean memorize, if you can understand that, then you understand the only single cash flow formula that exists. And I'll get into why I call it the only single cash flow formula that exists in just a minute. But first, let's add some notation. Okay, so this guy here, would that be the future value, you think, or the present value? That'd be the future value, right? And this guy here, would that be the present value or future value? That'd be present value, right? Now, does present value necessarily mean today? No, in reality, I mean, it might be today, but in reality, it's relative to the future value. So the present value really means an earlier value. Now, for this whole formula to make sense, 100 grows into 110, did we have to be working with effective rates? We did, right? So in other words, if these were 6-month periods, then this 10% better represent an effective what? 6-month rate. Okay. So if we put it all together, as far as the only single cash flow formula that exists, is we've got basically the future value equals present value times 1 plus r to the t. Where the 121 is the future or later value, the 100 is the present value or earlier value. We better be working with effective rates, and of course, in this case, we brought the $100 forward 2 time periods, which is what the t represents. So, like I said, this is the only single cash flow formula that exists. Okay, you're going to get problems and questions maybe in text, and in the end, they may rearrange this formula, or in textbooks they may rearrange this formula, and they might make it seem more complicated than it really is. But any of those other formulas that are out there are basically an algebraic rearrangement of this guy right here. In other words, I or anybody else, they should be able to give you any three of these, but notice there are how many variables? There's 1, 2, 3, 4. They should be able to give you any three, and you should be able to solve for the other. So what does this do? Well, you can move cash forward and backwards in time. If you move it back in time, it's called discounting. If you move it forward in time, there's no single word that I'm aware of, they're just taking the future value of. And I would argue that there's only one trap in this formula. And believe it or not, even though you have probably already demonstrated that you understand this formula, you might fall into this trap. Can you think of a trap? Well, basically, the R and the T have to, if you will, correspond or match, if you will. Now, what do you think I mean by that? Well, if these are 6-month periods, then you better be working with an effective what? 6-month rate, which means what? The amount of interest, go ahead, finish the sentence, made from $1 after 6 months, right? If these are 3-month periods, so from here to here is a 3-month period, then you'd better be working with what right here? An effective 3-month rate, which means what? The amount of interest made from $1 after 3 months. So, as I said, with a little algebra, you should be able to rearrange those and solve for any approach. Solve for any of these other variables, for example. And a general approach, and even I do this. After dealing with this stuff for years and years, that challenging problem that I showed you at the beginning, I could not do this by step 1 before you do any finance whatsoever. Take a stand on the interpretation of the problem. And how do you take a stand on the interpretation of the problem? Well, you draw a cash flow timeline diagram. And then, and only then, do you get into the finance and solve the problem. And so what we'll do is we'll go through some examples. And in the end, what you're going to find out with these examples is all I've done is I've provided 3 of these variables, and we've basically solved for the 4th. So let's begin with example number 1, where we're solving for an effective rate. So let's say a bank pays 12% compounded quarterly. Now, by the way, first of all, that 12%, is that already an effective rate, or is that an annual or stated or advertised rate? Well, that's an annual or stated or advertised rate, right? And so, because it doesn't say it's an effective rate, so by convention. So the question is, well, what's the equivalent 6-month effective rate? Now, not by understanding, but by definition, what is the only first step that I can do with this 12%? Divide it by 4, right? There's nothing else I can do as a first step. And then once I've divided by 4, in this case the answer is 3%, then what does that tell me? What does that 3% mean? Well, it's basically the effective quarterly rate, right? This would be the amount of interest made from $1 after 1 quarter. Okay? Now, the problem says, well, we want an effective 6-month rate. Well, what does that mean? What is an effective 6-month rate? The amount of interest, go ahead, made from $1 after 6 months, right? So, if we use what we already know is an effective quarterly rate, so we know that $1 grows into $1.03 after 1 quarter, could we use a single cash flow principles to figure out how much it grows into after 2 quarters, which, by the way, is also 6 months? We could, right? And that's our goal. We want to figure out the effective 6-month rate. So if the dollar grew into, say, I'll make something up, $1.08 after 6 months, then what would be the effective 6-month rate? 8%, right? I mean, that's not the actual number, but let's go ahead and figure it out. So here's the only single cash flow formula exists. So what do I put in for future value, FV? Well, that's what we're trying to figure out, right? Here's the future value right here. What do I put in for PV? Well, that'd be $1, right? I mean, there's a couple different ways you could do it. It could be $1 and you move it forward 2 periods, or I guess you could also begin with $1.03 and you move it forward 1 period. Doesn't matter. Either way, you'll still get the same answer. Okay, what's the R? Well, how long are these periods? They're quarters, right? So I better be working with what kind of effective rate? An effective quarterly rate, right? And we already calculated that. That was how much, you remember? That was 3%, right? So if I put $1 here, then what do I put in for t? How many periods am I moving forward this $1? 2 periods, right? So if we calculate that, then we'd get the future value of this $1. It grows into 1.0609. And so what is the effective 6-month rate? Well, how much of this 1.0609 is interest? Well, 0.0609, right? And so therefore the effective 6-month rate is 0.0609 or 6.09%. By the way, when you're working with these formulas, would I ever work with this 6.09, this number right here? I wouldn't, right? Because that's just an English way of representing what is shown here mathematically. What does percent mean? It means divided by 100. So when I'm speaking English to you and I go 6.09%, when I use that in formulas, well, I take this 6.09 and I divide it by 100, which is what we get here, and that's what we use in formulas. This is the mathematical language, if you will, while this over here is the English language. So let's do another one. A bank pays 12% compounded quarterly. What is the equivalent monthly effective rate? Now again, what is the only first step that I can take with that 12%? Divide it by 4, right? Because it says 12% compounded quarterly. How many quarters in a year? 4, right? And this 12% by convention is annual. So the only first step I can do with that is divide it by 4. And as we've already seen, that means that basically the effective quarterly rate is 3%. Or in other words, $1 grows into $1.03. Now this problem wants the effective 1-month rate. So what's the definition of an effective 1-month rate? Well, the amount of interest made from $1 after 1 month, right? So if we go back, we know that $1 grows into how much? Do you remember after 1 quarter? $1.03, right? We just calculated the effective quarterly rate, right? Now how many months in a quarter? 3, right? So in other words, another way of looking at this is that we know that if we begin with $1, that after 3 months, it better grow to $1.03. That's our benchmark, if you will. So the question is, does there exist an effective monthly rate such that $1 after monthly compounding will grow into $1.03? It does, right? And is this a single cash flow problem? It is, right? So which numbers will go where? Okay, here's the only single cash flow formula that exists. What will I put in for my future value? Well, the 1.03, right? What about my present value? 1, right? What about my R? Well, that's what we're trying to figure out, right? That's the effective monthly rate. And then what about my T? How many periods am I moving forward this $1? 3, right? And so this is nothing more than another single cash flow problem. So if we put in those numbers, here's the future value, the 1.03. Here's the present value, the 1. I'm solving for effective monthly rate. Here I have 3. I'm bringing it forward 3 times. And if you do the algebra, then you would solve for the effective monthly rate being 0.99%. Now I'm not typically going to do the algebra because it's a finance class, but just in case it's helpful, I'll go ahead and do it this time. Okay, so there's the formula. Sorry, my writing is not that good. So what I'm going to do is I'm going to take the cube root on each side. Okay, so 1.03 equals 1 plus m. Okay, so this will be the cube root to the third, and this will be 3 over 3 to the third, so that just goes away. So we got 1.03 to the third, and then I'll equals 1 plus Rm, and I'm trying to solve for the Rm right here, right? And so I'll just subtract 1 on each side, so 1.03 to the third, or 0.3333 minus the 1 is going to be our Rm. So that's the algebra. But like I said, I won't typically be doing the algebra in most of these things. So, any case, that's another example. And by the way, okay, so that's the another example of effective annual rate. And in both cases, both the first example and the second example, did we use that single cash flow problem? We did, right? And so therefore you can solve this stuff with just that single cash flow problem, the one that you already illustrated to me that you understood. Okay? And yet, again, as I mentioned, if you go to textbooks, they're going to have these complicated looking formulas, and they're going to call this, well, this is our effective annual rate formula. All right, well, don't memorize those. You don't need those, because as I've just demonstrated to you, if you understand the only single cash flow formula exists, then you can do all of these problems based just on that, at least all these effective annual rate problems. So let's do another example, moving cash forwards and backwards. So let's say you inherit $10,000 that's payable in 6 months. And the question is, what is the equivalent value 3 months from today? And what is the equivalent value 1 year from today? Assume a bank pays 12% compounded monthly. Now, what's the first thing I'm going to do before I do any finance whatsoever? How am I going to take a stand on the interpretation of the problem? Well, I want to draw a cash flow timeline diagram, right? Now, what do my periods have to be? Well, when does some kind of action happen with the cash flows? Well, months, right? I mean, this is monthly compounding, and that's the primary thing. I'm getting this stuff in months. So basically, if I draw the cash flow timeline diagram, I'm going to have, if I call 0 today, okay, then the 10,000 will show up at what time period? Time period 6. And the question is, well, what is it 3 months from today? If this is time 0 today, then what is it worth 3 months today? And what is it worth 1 year or 12 months from today? So what kind of rate do we need? Well, we need an effective monthly rate, right? And the question says, all right, well, 12% compounded monthly. Now, is this already an effective rate? It's not, right? Unless it tells you, hey, this is an effective rate. You have to assume that it's what? APR, okay? Or stated rate, or nominal rate, okay? So what's the only first step that I can do with that guy? Divide it by 12, right? That's by definition. It's not by understanding. As I mentioned, that's by definition. So divide it by 12, and now what do I have? Well, by definition, I now have my effective monthly rate, which is what we wanted. And so let's start off with this guy. What is the value of the 10,000 at time 12? Okay. Well, what would be my FV? Well, that's what we're trying to figure out, right? It's the later time period. What would be my PV? It would be the 10,000. What would be my R? Remember, these are monthly periods, so I better be working with an effective what? Effective monthly rate, right? And so what would be my T? Well, how many periods am I moving this forward? 6, right? So what would be my T? Be 6, right? So then basically we have this amount is what it's worth at time 12. So here's my question, okay? Given the effective rate, okay, if we don't change that, then what would you rather have? Would you rather have the 10,000 at time 6 or this amount at time 12? Well, You might say, well, I'd rather have the 10,000 at time 6 because maybe I want to go spend it, or I'd rather have this much at time 12 because that looks like a bigger amount of money and I just feel richer that way. And all of those are sort of personal, maybe emotional reasons. But which is fine. I'm not, putting that down. However, having said that, from a mathematical point of view, and given the rates that we made up, are these two mathematically exactly identically equivalent? They are, right? And that's what time value money does for you. Okay? So mathematically, you'd be indifferent between those two, given the rates that we made up. Now the question also asks, well, what is this worth 3 months from today? So here's today, so that's 3 months today. So in other words, we've got to bring this back in time. Okay, so again, if I just rearrange this formula, divide both sides by 1 plus r to the t, I get present value. I'm dividing by something, so we're discounting. And so basically, what would go right here for my future value? Okay, well, that'd be the later value, right? Would the later value be what we're calculating, or what this 10,000 is? Be what the 10,000 is, right? And what kind of rate had I better use? Again, effective monthly rate, right? And how many periods am I going back? 1, 2, 3. So what do I put here? 3, right? And so basically, we have this 97.05 is what it's worth at time 3. So again, what would you rather have? Would you rather have 10,000 at time 6 or this much at time 3? Or, from a mathematical perspective, would you be indifferent? Well, from a mathematical perspective, you'd be indifferent, right? Given the rate, they are mathematically exactly identically equivalent. Okay, so essentially we've solved for 3 out of the 4 variables. Remember, future value equals present value times 1 plus r to the t. So we've solved for a future value, we've solved for a present value, we've solved for a couple of different r's, effective annual rates. So there's only one left, and that's t. However, fasten your seatbelts. We need a mathematical identity to solve for t. And what do I mean by that? Well, we're going to use a characteristic of a mathematical function to help us solve for t. Now, what's a mathematical function? Well, y equals 2x, right? So put in a number for x, say the number 2, so 2 times 2 is 4. So there's also a function called the logarithm, okay? And you can work with what you'll see is LOGs, maybe on your calculator, which are base 10 logs, or you can work with natural logs. ln is natural logs. And basically, a logarithm is nothing more than a mathematical function, but it has a particular property, okay? And the property it has is that when you take the log on each side of an equation, okay, if you have something like, say, x to the t, you can take this t and you can bring it and put it in front. So in other words, this t, this guy right here, is the same as t multiplied by log x, okay? Or if they're natural logs on this side here, this guy right here is the same as t multiplied by the natural log of x. So for example, okay, and the best way to convince yourself of this is just go to your calculator and prove this to yourself, okay? So we could work with maybe natural logs, okay, just to illustrate. Well, what's 10 squared? It's 100, right? So if in your calculator you put in 100 and then you push that ln button, you're going to get about 4.6, okay? Now, if you do the same thing with the number 10, put in 10, then the natural logarithm, you're going to get 2.3, roughly, okay? Well, what's 2 multiplied by 2.3? It's 4.6, right? So this is just a function that has this characteristic where if you have something that is to an exponent, you can bring it down and put it in front. And so just convince yourself, if you like, convince yourself with the LOG button on your calculator if you have such a guy. And we're going to need that characteristic to solve for t. So let's go ahead and do it. Let's say you have a balance of $100 in your account And the question is, well, how long before it triples in value if a bank pays 12% compounded semi-annually? Now, before I do any finance whatsoever, what am I going to do first? I want to picture what's going on. I'm going to draw a cash flow timeline diagram. Okay? So if I do that, then basically I have $100 at time 0. I've got semi-annual compounding. So what do these periods have to be? When does some kind of action happen with the cash flows? Every 6 months, right? So they're going to be semi-annual periods. And what should the future value be for this problem? Okay, so we're trying to solve for t. The question says how long before it triples. So if the $100 is tripled, then what are we going to put in here? 300, right? And as I've already mentioned, the periods in this diagram, 6-month periods, right? Some kind of action happens with the cash flows every 6 months. So if these are 6-month periods, then we better be working with what kind of rate? An effective 6-month rate, right? Which again means what? The amount of interest made from $1 after 6 months. So let's go ahead and look at that. Well, what is the effective 6-month rate? It said 12% compounded semi-annually. So what's the only first step I can do with that 12%? Divided by 2, right? And so 6% is my effective 6-month rate. So if I now apply the formula, what's my future value? It's 300, right? What's my present value? It's the 100, right? What's my R given these are 6-month periods? It's my effective 6-month rate, right? Or 6%. And what's my T? Well, that's what we're solving for, right? How long before it triples? Okay, so basically that would be what we'd put in for our single cash flow problem. So if I divide both sides by 100, I basically get, this. So 300 divided by 100 is what? 3, right? Now, if I want to, can I take the log on each side? Well, in algebra, whatever you do to one side, you also do the same thing on the other side? You do, right? And again, it doesn't matter if I take the log on each side or the ln, as long as you're consistent. But I'm gonna use the logarithm function because I somehow need to get this t down. So in this example, I'll use the natural log. Okay. So what can I do with this t because of the log function? Well, I can put it in front, right? That's the same as t multiplied by the natural log of 1.06. So if I divide both sides by the natural log of 1.06, then I get what my t is. So if you just go to your calculator and natural log 1.03 and then put in the natural log 1.06, you'd get about 19 periods. So does that mean that it takes 19 years for this $100 to triple? No. 19 periods, right? Well, how long are these periods? They're 6-month periods, right? So basically, there's about 19 6-month periods. So how many years is that? Well, that's about, what, 9.5 years, right? So it takes about 9.5 years for this thing to triple. So that's basically single cash flow principles. And you should really get solid on it. I mean, practice a few of these. I mean, go to a textbook or look up online some problems and practice these and get really, really solid if you're not already solid before you do part 2A, lecture 2A, because lecture 2A is going to build on this stuff, okay? And I'm going to assume as I get into that lecture that you have a solid understanding of this. In any case, I hope this was helpful, and hopefully I'll see you at the next lecture. Take care. Bye-bye.